It is my great pleasure to welcome the audience to my sedimentology lunch presentation today. During the following 45 minutes, I will provide you some interesting insights into a collaborative 5-year research project on the Great Blue Hole sediment succession, which was founded by the Deutsche Forschungsgemeinschaft. The here pictured sinkhole was investigated as a unique sedimentary archive for the reconstruction of tropical Atlantic cyclone frequency and southwestern Caribbean sea surface temperatures in this project. I would like to open my talk with a brief question to the audience. Why should we as geoscientists systematically study the history of tropical storms and hurricanes? In this context, a few pictures are sometimes worth 1,000 words. Such kind of paleoclimate studies achieved in the past few years a really booming scientific and public perception, considering the omnipresent climate change discussion and steadily increasing concerns about the problems of global warming and its reinforcing effect on worldwide environmental disasters. Despite all recent advances that have been made in the field of climate research, the modeling of future climate scenarios remains still one of the greatest challenges of our time. We as geoscientists can make decisive contributions to handle this challenge with paleoclimate studies on new climate-sensitive sedimentary archives. Let us first start by looking at what we know from the last 115 years of instrumental data measurements. This graph here shows that the frequency of tropical cyclones has increased in the tropical Atlantic region from an average of 6 to 12 storms each year, following a clearly visible multi-decadal pattern with 3 maxima and equal minima. The consideration of the meteorological record might indicate that a continuation of further rising sea surface temperatures could keep the Atlantic storminess at the current high frequency state or push them probably even higher above. Or if not, maybe we are wrong. They could indicate a shift towards a more frequent formation of major hurricanes of categories 4 and 5. As you can see on this figure, the formation of pink and purple colored major hurricanes seems to increase over the last decades. So to conclude, what did we learn from the instrumental measurements? The storm strength or the storm frequency could likely increase in a future greenhouse climate. This alarming forecast involves, of course, an elevated probability of ecological and social disasters for circum-Caribbean countries, which were already tragically exemplified by several exceptional severe hurricane strikes during the past 20 years. This future scenario is indeed based on reliable climate data from the instrumental era, but all these measured data sets have one crucial limitation: only 150 years of data availability. Many control factors of the global climate system operate, however, in time intervals, usually covering several decades, sometimes multiple centuries, and in some cases even whole millenniums. Considering a 115 years short record alone can consequently only offer a limited perspective for understanding the Earth's complex climate system. Our research project on the Great Blue Hole contributes to extend the high-resolution climate research up to a 12,000 years long perspective spanning the entire Holocene interglacial stage and even parts of the late Pleistocene. But what are the advantages of using sediment sequences from marine blue holes? Such structures offer an exceptional potential for long-term climate reconstructions. And the Caribbean region is in addition a very climate-sensitive region and well suited to study Holocene climate variations and different climate phenomena. some words to these climate phenomena. The El Nino southern oscillation is a coupled ocean and atmosphere feature that primarily operates in the equatorial Pacific, but there are also important teleconnections with the tropical Atlantic, affecting, for example, cyclone frequency on multi-annual timescales. The North Atlantic oscillation is a measure for air pressure gradient fluctuations between the Icelandic low and the Azores high, and it is supposed to be a key mechanism of the North Atlantic atmospheric circulation, which influences the track pathways of tropical cyclones. The Atlantic multidecadal oscillation is another major oceanographic feature of climate variability in the North Atlantic that modulates sea surface temperature and precipitation on multidecadal timescales. Throughout my lecture, I would like to follow a common thread and answer further on 4 major questions. First, what paleoecological conditions existed over the last 12,000 years? Second, how did the tropical cyclone frequency vary in the southwestern Caribbean over Holocene time series? Third, does the Great Blue Hole Sediment Archive tracks climate changes and sea surface temperature variability? And last but not least, is this sinkhole succession a new archive for the detection of climate phenomenon signals? Let me first say some words about the study area. Belize is a Central American country bordered by the Mexican Yucatan Peninsula, Honduras, Guatemala, and the Caribbean Sea. The 3 carbonate platforms of Turnip Islands, Glover's Reef, and Lighthouse Reef, formed together with the Belize Barrier Reef, one of the largest interconnected modern reef systems. Lighthouse Reef is with 200 square kilometers, the smallest of the 3 Belizean offshore atolls. The atoll is geomorphologically characterized by an up to 8 meters deep eastern lagoon, separated from the shallower western one by a 20 kilometers long chain of coalescing coral patch reefs. It has a discontinuous leeward and a continuous seaward surface breaking reef rim with sloping forereefs. Behind the windward eastern reef, you can see white sand aprons. The Great Blue Hole is a circular and inundated former terrestrial karst cavern of Pleistocene age, which is highlighted in the far right-hand picture. The Great Blue Hole itself has a diameter of 320 meters, a depth of 125 meters, and it is almost completely surrounded by a ring of coral reefs, except for 2 channels in the east and northeast. Because of its location in the Atlantic hurricane belt, the cavern works like a giant sediment trap, which captures coarse allochthonous carbonate particles produced by marginal reef erosion through incoming storm waves and surges. A passing cyclone causes a noteworthy particle overwash, which leads in combination with a sinkhole slope destabilization, sediment density flows, and a suspensional fallout to the formation of a visible event bed that emerges as a coarse layer from the very fine fair weather sediments. The sediment succession is due to seasonal productivity fluctuations, annually varved, and because of anoxic bottom water conditions completely undisturbed. That means the sediments are not affected by bioturbation and or other physical processes of sediment reworking, and thus well suited for high resolution cyclone and sea surface temperature research. Our 2 expeditions to Lighthouse Reef were in August 2017 and May 2022. Our drill team collected 8 cores from the bottom of the cavern. During the 2017 fieldwork campaign, we used our working group's own portable Rosfelder P3 electrical vibrocorer system, which is pictured on the left side, in order to core 7 up to 8.5 meter long cores, which is the maximum length of that method we could handle. In the second fieldwork campaign, we were able to core a 30 meters long core with the UVTech single corer platform system of Professor Martin Mellis from the University of Cologne. The platform system is pictured on the right side. In the first main section of my presentation, I would like to talk a bit about the sedimentological results of the study, which allowed us to reconstruct the paleoecological history of the Great Blue Hole. This requires at first, of course, a robust age model. The chronology of the core BH8 is anchored on two well-established and independent age depth frameworks. For the age dating, we used a combination of 14C AMS radiocarbon and WRF age models. You can see that both applications show a very strong linear correlation with a significant age offset appearing only in the middle core parts. There, the WRF counting approach was very difficult and is largely extrapolated because of larger core catcher segments with a lack of intact WRFs. We supportive offer a pollen-based core top dating covering the instrumental record or the historical record that relies on increased abundances of corn, pine, and palm pollen, which all provide evidences of past recent anthropogenic plantings. Our core analysis enables past ecology, cyclone, and sea surface temperature reconstructions with annual resolution throughout the entire Holocene and parts of the late Pleistocene back to 12.5 kiloannuals before present. Just for comparison, the majority of existing sinkhole studies target at maximum common error scale, what means the past 2,000 years. The sediment package of the Great Blue Hole comprises from top to bottom full marine carbonates, brackish carbonates, and more organic-rich carbonate sediments. This is an R. Bacon-based radiocarbon age model that illustrates that the sinkhole succession can be divided into three major units based on different sedimentation rates and sedimentological variations in the core. If you have a closer look at the three illustrative facies examples on the bottom, you can see that there is a buff green beige section from the core top down to 24.6 meters, a darker green-brown part further down to 28.6 meters, and a succession of brown to almost black organic-rich sediments, which are more terrestrially influenced down to the core base at 30 meters. From our pollen and sediment studies, it can be reconstructed that the carbonate platform was subearly exposed during the late Pleistocene and early Holocene. Between 12.5 and 7.2 kiloannuals before present, Lighthouse Reef was supposedly covered by a Myrtacea-dominated neotropical forest. At that time, the Great Blue Hole was likely reminiscent of today's coastal terrestrial cenotes, what are mixed fresh seawater-filled karst caverns, which are known from the Mexican Yucatan Peninsula. Between 7.2 to 5.7 kiloannuals before present, the mid-Holocene sea level rise gradually inundated the platform. At that time, pollen from the red mangroves Rhizophora were found very often besides other frequent beach herb and fern pollen, for example, Acrostichum. The platform ecology was likely similar to those of today's neighboring Turneffe Islands atoll with a lot of mangrove forest and small islands. The environment around the Great Blue Hole may have been comparable with the pictured Meredith Blue Hole on Great Abaco Islands on the Bahamas, including the mentioned local mangrove forest, shallow inundated marsh islands, and local swampy areas. The present ecology and morphology of Lighthouse Reef, facilitating a full marine blue hole, was reached due to a further rising sea level in times younger than 5.7 kiloannuals before present. After this time, the last mangrove pollen completely disappeared. Only wind-carried pollen from oaks and pines could be detected with higher abundances. After this core sedimentology and pollen analysis excursion, I would now like to slowly move on to the second topic of my presentation. The Atlantic cyclone formation takes place in the so-called hurricane main development region. Kossen et al. Subdivided this area into 4 different clusters of main storm genesis. Tropical cyclones are without doubt extreme weather events with a huge potential for environmental, social, and ecological hazards. It is therefore very important to understand the causes of storm frequency changes on longer than the short instrumental records. The formation of such violent storm systems strongly depends on surface water temperatures above 26.5 degrees Celsius and some other important atmospheric boundary conditions. During a progressive storm intensification, we call the initial anomaly a tropical wave, then a disturbance. Afterwards, it is called an investigation, a tropical depression, and finally, a tropical storm or a hurricane. The last one is again subdivided by the Saffir-Simpson hurricane scale into 5 categories depending on the maximum wind speed. Cyclogenesis starts when humid air begins to rise upwards over tropical ocean sites with constant temperatures above the critical threshold. As a result, a low-pressure disturbance is formed. While the updrafted air mass condenses, poorly organized thunderstorm clusters start to form. From surrounding high-pressure areas, more warm and moist air flows into this low-pressure cell, causing a repetitive cycle, mandatory for the further storm intensification. With a constant fuel supply of rising warm, moist air in the wake of an ongoing evaporation, a better organized storm system starts to form. The rotation of the Earth, or better, the Coriolis effect, forces the gradually self-organizing storm systems to spin counterclockwise on the northern hemisphere. The rotating thunderstorm clusters begin to form very well-organized spiral rain bands around a cloudless eye, transporting heat 15 kilometers or higher into the atmosphere. Some of the drier and cooler air sinks back into the low-pressure region at the center of the cyclone, hence causing the relatively calm eye. The majority of the cool air spirals outward, away from the cyclone center, and sinks back down to the bottom in the regions between the individual rain bands. If the environmental conditions constantly support the heat engine of storm, then a tropical cyclone can maintain its organized structure over several days. But how exactly do the remnants of such storm systems look like in the sedimentary record? And how did we identify them? On this picture, you can see that the internal core stratigraphy of BH8 is bipartite and includes greenish dwarf fair weather deposits and brighter yellow-brown cyclone event layers intercalating them. As an improvement to comparable cyclone frequency studies, our project team applied a multi-proxy approach to ensure a more reliable identification, considering, for example, sediment texture, composition, and geochemistry. 2 further highlights are the integration of high-resolution XRF scanning datasets and grayscale measurements of radiographic core images. These 2 methods were developed as new tropical cyclone identification tools usable in such calcitic sinkhole environments. Both new methods are very sensitive to record changes in a calcitic fair weather versus an aragonitic cyclone overwash sedimentation. Event layers typically show a higher strontium to calcium ratio and a lower gray value. On this slide, I will use exemplary the uppermost core log section for explaining how the event layer identification was done in detail. We started with a visual core investigation. Around 700 potential event layer and 60 fair weather samples were analyzed. Storm layers have been classically determined by quantitative textural analysis, resulting in thresholds for minimum amounts of coarse fractions larger than 63 micrometers and a minimum mean grain size value. Positive peaks in the strontium to calcium and negative ones in the grayscale records have been used hereafter supportive to identify the individual storm layers. But since we are still waiting for some remeasurements, this part of the approach is right now a work in progress, though I can't present a cutoff like I did for the fraction larger than 63 micrometers or the mean grain size. To complete our multi-proxy approach, the thickness of individual layers, color measurements, and even compositional facies observations with thin sections have been also considered for a reliable identification of an event bed. For a safe identification, it requires at best match to fulfill several of the different identification criteria. A data comparison with the historical record, that means the last 150 years, suggests that our cyclone archive is generally sensitive to all storm categories, ranging up from tropical storms to major hurricanes of categories 4 and 5. Since 1950, 83% of all tropical cyclones that have passed Lighthouse Reef were recovered in the sediment succession of the sinkhole. Our data comparison also indicates that it makes a huge difference whether a storm system passes north, central, or south of the sinkhole. With a success rate of more than 91%, nearly all south traversing storm systems were recovered in the sedimentary record. The centrally or northerly crossing storm systems were obtained much less often, with 67 or 75% respectively. After a data evaluation, we are convinced that these differences are related to the sinkhole morphology and the rotation of storm systems on the northern hemisphere. The channel openings to the east and northeast make a storm layer deposit much more likely for south trending storm systems with a counterclockwise rotation. On this slide, you can see now our final cyclone frequency reconstruction, indicated by the black pillars on the bottom of this figure. The BH8 records exceeds all previous Great Blue Hole records by far and highlights a first interval of clearly elevated tropical cyclone activity in the expiring Holocene climate optimum. This period of very high storm activity emerges from a 5,500 years long period of strongly diminished storm activity. The brief mid-Holocene peak phase is followed by a longer plateau of, I would say, medium activity, culminating in another high-frequency interval during the so-called Minoan warm period. Since about 3.5 kiloannuals before present, another stepwise increase towards a generally higher storm activity stage occurs, with two more outstanding maxima. The first during the medieval warm period, and the second in the present-day industrial warms. And it seems that this increasing trend will definitely speed up in the future. To highlight the most important result for you, the southwestern Caribbean storm frequency changed naturally from a less active to a more active stage since the mid-Holocene. But we clearly see that there is an anthropogenic effect amplifying the frequency of tropical storms since about 50 years. So the most important question is, what could be the driving force behind the natural storm regime change? Is it temperature or maybe something different? If you concentrate on the red curve first, you can see that there is some kind of an antiphase pattern between our tropical cyclone activity reconstruction and the very famous global mean surface temperature of Marcotte et al. The noteworthy temperature decline starting in the mid-Holocene is called the neoglacial cooling, which culminates in the Little Ice Age, which lasted from around 1400 to 1800. Interestingly, this 1.2 degrees Celsius neoglacial cooling is not really reflected in our frequency data, which show an increase. But if you consider the green profile now, indicating on the contrary a gradual sea surface temperature rise during the Holocene, then you will agree that the simulated and largely CO2-based temperature curve fits better with our storm data. But even this computer simulation can only partially explain the observed storm variability. The discrepancy between proxy models and computer simulations is known as the Holocene temperature conundrum, which is still one of the very few controversial discussions within the geoscientific community. Under this circumstance, it is very difficult for us to prove whether the sea surface temperature variability is the major driver for long-term shifts. I should add, without a coherent new local sea surface temperature curve, but more on that topic later in my talk. So let us look closer at the last 2000 years and consider some other regional storm activity reconstructions in order to discuss another potential driver. We have seen that the BH8 cyclone record coincides quite well with previous ones from the Belize atolls. Most of the Belizean offshore cores indicate the highest activity during the present global warming. A distinct decrease back to, I would say, medium activity during the Little Ice Age, and then again, a very high activity throughout the medieval warm period, which is surprisingly comparable with the present one. A coastal lagoon record from Puerto Rico shows an activity pattern, which is overall relatively comparable to those of Belize. But another lagoon record from the Northern Antilles demonstrates a different behavior of common era storm frequency. And more in the northern, two North American records differ completely from all the other ones located in the south. Considering this, we concluded that not only the differences between northern and southern archives, but also the Holocene variability received from our new core analysis can be perhaps good explained by latitudinal changes of the intertropical convergency zone. Atlantic cyclones develop along the northern edge of the intertropical convergency zone and move on in a west and northwest direction towards the North American East Coast. A latitudinal intertropical convergency migration causes a shift of the cyclone genesis regions, which of course would affect the common storm tracks and the landfall sites. Now please have a closer look at the black curve in the figure you know from a few slides ago. A more northern position of the intertropical convergency zone was reconstructed in the early to middle Holocene. The ITCZ then shifted from 4 to 3.5 kiloannals before present from this relatively northern position towards a more southern location. And remember, with a more southern located Genesis region, storm systems following the typical west-northwestern directed tracks would tend more likely to pass over the study site in Belize than with a more northern one, which would induce more frequent landfalls in far northern regions. This pattern of a continued southward ITCZ movement agrees well with the regional differences between the North American and the Caribbean records, and also with our Holocene frequency reconstruction, indicating an antiphase change of activity from low to high. We have now talked some time about storm frequency reconstructions. But what about the strength of cyclones and the predicted shift to higher storm intensities mentioned at the beginning of my talk? Is there a way to reconstruct also the intensity in the past? This is, to be honest, very challenging. And such a proxy may be called the holy grail of storm research or something like this. But nevertheless, we tried to develop such a proxy. The textural data of 32 cyclone event beds from the historical record back to 1950 have been compared with instrumental data of wind speed at the location, storm duration, and the distance between storm track and study site. We indeed found out that all three textural parameters show a very high statistically significant correlation with the wind speed at the study site, or better, the storm intensity. But 30 cyclones of 6 different categories, including tropical storms and major hurricanes, provide unfortunately still not enough trustful data to present a valid proxy for past storm intensity reconstruction. This would require a much longer instrumental data series and more individual storms for each category. Let us now move on to the third part of my presentation. I would like to present you some insights into what we have planned in the next year. So far, many climate reconstruction approaches in the Caribbean region derive mostly from terrestrial lake or speleothem records, with a focus only on local precipitation patterns and Pleistocene perspectives. All these approaches are, however, of course, not sufficient, particularly when considering our oceanographic objectives in the Holocene. The 30 meters long sediment core, BH8, offers now the great opportunity to continue with our initial research efforts on creating an outstanding tropical Atlantic sea surface temperature record. This slide is an exemplary overview about which sea surface temperature records are currently available for the Atlantic Ocean. Most of the existing sea surface temperature records have been obtained from relatively short sclerosponge, foraminifer, and coral archives. Ocean temperature reconstructions, fully covering Common Era and Holocene time series, are almost exclusively smooth synthesis approaches, compiling several of the short and regional Atlantic records to a single and continuous temperature curves. The planned analysis of the new core provides the unique possibility for us to develop a continuous Holocene record from a single location for the tropical Western Atlantic. This is a great advance compared to the compiled records created by slicing individual records from very different regions and environments. We already successfully tested a combination of geochemical and molecular proxy methods in order to create a 2,000 years long Common Era temperature record. For stable isotope analysis, the core bulk material was continuously sampled at annual resolution through 8.5 meters of warped core sections. The oxygen isotope data were used to reconstruct a relative sea surface temperature curve. A 2.5 millimeter slab of bulk material was discretely sampled every 10 centimeters within the fair weather sediments to achieve a 14 years resolution of TEX 86 data. The relative abundances of GDGTs were analyzed from our colleagues in Hamburg to calculate the TEX 86 index as a salinity-independent proxy for absolute sea surface temperature values, using the shown TEX 86 calibration of Kim et al. Adopted for subtropical environments. These geochemical analyses were carried out to estimate the role of sea surface temperature within a positive feedback of climate variability and storm frequency. The shown high-resolution delta 18O curve is supplemented at its top with absolute temperature values using the TEX 86 application. Over the past 2,000 years, both data sets imply a general temperature rise of about 1.3 degrees Celsius, which is again accompanied by obvious multi-decadal fluctuations. You will remember that this result does not coincide well with the famous Marquardt reconstruction. In our record, there is not really a cooling trend visible in the Little Ice Age, which is proposed to be the maximum of the neoglacial. It looks more like that the local ocean temperature strongly rises since the beginning of the medieval warm period, what is, as you remember, better shown by the Liu et al. Simulation. However, the regional temperatures were, despite of a visible variability, for most of the time higher than the critical threshold necessary for a very frequent formation of tropical cyclones. We now plan to extend this curve up to a coherent record for the entire Holocene interglacial next year. This will hopefully allow us to collect more data to answer the open questions in the cyclone topic, and it may finally also help us to solve the Holocene temperature conundrum. In addition to the delta 18O measurements, delta 13C values were also measured by our in-house stable isotope laboratory. The here presented carbon isotope record exhibits two remarkable negative anomalies and an overlying upcore decreasing trend. Some authors explain such negative carbon isotope excursions and following stable plateaus with an intensive Mayan deforestation. That means an increased 12C export through soil erosion, and later on a forest regrowth with an attenuated 12C export. Right before the first drop, Central America saw proliferation phase of the classic Mayan civilization in consequence of challenging climate conditions with strong rainfalls, multiple dry phases, and overall more cyclone landfalls, which may lead to a first collapse. Some archaeological evidences indicate that many of the large thousandly located pre-classic Mayan centers were abandoned around this time, probably due to this past climate change. The development of new cultural centers in the north and the creation of new farmland lead to a subsequent deforestation of large areas in Belize, what may have caused the carbon isotope anomaly with a certain delay. Our new pollen analysis provide supportive evidences for the role of the Mayan civilization. Many charcoal residues were found in the blue hole sediments, especially during the peak phases of the pre-classic and classic Mayan culture. These charcoal residues could have been produced during fire clearing the tropical vegetation or during limestone processing for construction work on cities and religious buildings. The older drop in our delta 13C values is therefore assuredly attributable to vegetation and soil erosion changes caused by an ancient civilization. We attributed the younger drop starting around 1900s to the industrialization and the Suez effect. This is another example of how the influence of humans sustainably influenced the carbon cycle. Finally, I would like to talk a bit about those obvious multidecadal fluctuations we had seen in the oxygen isotope record, which reflect probably a multidecadal climate phenomenon influence. In a previous study, we were able to show that 3 positive and 2 negative AMO, means the Atlantic multidecadal oscillation, correlated with high and low cyclone frequency intervals during the short instrumental era. Within the past 115 years, there is a clear evidence for higher tropical cyclone frequency during positive AMO phases in which a higher sea surface temperature prevails in the cyclone main development region, and vice versa. Based on these findings, we hypothesized that the storm frequency of the Atlantic could potentially underlie a multidecadal AMO control over common era, or even over Holocene timescales. Many of the existing AMO records are, however, only based on single tree ring archives or coral skeletons, which do, of course, not continuously record such signals over about 12,000 years. But the new BH8 archive, of course, has the potential to prove the appearance of AMO phase changes over such a long timescale. We attempted to investigate our delta 18O data with a wavelet spectral analysis. This statistical analysis allowed us to identify 2 statistical spectral peaks with multidecadal to centennial scaled periodicities. The shorter cycle occurs with 32 to 64 years, and it's therefore either compatible with the periodicity of the AMO or variations of ENSO amplitudes. We suspect the AMO phase change to be an appropriate driver for the multidecadal sea surface temperature modulation because of the historical record correlation of AMO variability, cyclone frequency data, and local sea surface temperature. the lack of intradecadal ENSO signals is another indirect argument for the proposed AMO phase change control and against an ENSO amplitude modulation. We tested the delta 18O fluctuations with XRD analysis and SIN sections to be independent of any compositional variations. The longer signal was more speculatively interpreted to be the result of solar irradiance cycles. To conclude, the AMO phenomenon is likely not only a major control factor for storm frequency in the instrumental era. Its influence reaches at least back into the Common Era, minimum to the year of 300 CE. Now I'm closing my talk with a summary of the most important points. Hopefully, the four major questions have been answered in a sufficiently comprehensible manner. I presented a brief paleoecological journey through the last 12,000 years, showing the development of the Great Blue Hole from a cenote on a subearly exposed limestone island covered by neotropic forest, over a brackish blue hole in a shallow inundated mangrove swamp to a full marine blue hole in a coral reef atoll. On this journey, we have learned that the storm activity of the southwestern Caribbean shifted from a less active to a more active state since the mid-Holocene, most likely because of a persistent latitudinal ITCZ movement to the south. We proved that it is possible to track past climate changes and local sea surface temperature variability by using geochemical and molecular proxy methods on sinkhole sediment successions. In this context, we succeeded to identify continuous and at least common era-long multi-decadal signals in the sea surface temperature records and aligns them to a climate phenomenon control of local sea surface temperature. At that point, I would like to thank the organizers for the invitation to present our research project in the Sedimentology Lunch Seminar. I would also like to take the opportunity to thank the DFG for several years of founding and the entire Great Blue Hole research team for realizing such a great and successful project over the past 4 years. If there are further questions, feel free to ask. Thank you very much for your attention.